Good morning, students. Mr. Carver here. Polar graphs today. Some special polar graphs, or common polar graphs. I think, mention that there's no calculus in this chapter. There actually is just a bit of calculus. We're going to go over how to find rectangular slope of these shapes once I'm through the review of just getting them graphed. So let's start talking. We'll start off with some easy ones and move into some more difficult ones. All right, so to begin with, let's do theta is equal to pi over 6. Theta is equal to pi over 6. I believe I went through this in the last video. I'll do it again quickly, though. It's pi over 6 regardless of r. So all the positive r's are going to take you out in this direction, and then all the negative r's, obviously, are going to back up, go in the other direction. So that's the graph of that equation right there. Likewise, if you've got something like r is equal to -3, that means the distance from the pole, and by the way, the pole is the origin in this case, distance from the pole is always -3 units, or I should say, regardless of the direction in which you point, you are always going to back the truck up 3 units. That's an r, not an x. It looks an awful lot like an x, so it's an r is equal to -3. So I'm pointing in the 0 direction, I back the truck up 3 units. That puts me right here. And then as I increase my theta from 0 to pi over 2 to pi, I'm just going to begin to trace out this circle right here. So it's a circle with a radius of 3. And that's that graph. All right, let's take a look at r sine theta is equal to 2. If you recall from the previous video, r sine of theta is equal to y. That's just y is equal to 2. This graph is equal to this graph. Obviously, I've just converted it from polar to rectangular. Y is equal to 2 is a horizontal line 2 units out. Looks something like this. So if I superimposed a rectangular coordinate system on top of this polar graphing system, they would occur at exactly the same position. Looks something like that. Now, there's a twist to this slightly. No pun intended, but if I have r cosine theta minus 5 pi over 6 is equal to 4, and I just for the time being, just disregard this portion right here, then this expression right there is x is equal to 4. So if I start out, x is equal to 4, I'm 4 units to the right, 1, 2, 3, 4, looks something like this. Now, if you think about this portion of the expression, or the equation rather, right here, theta minus 5 pi over 6, this behaves in a similar fashion to how shifts work in rectangular form. That is, 5 pi over 6 is a rotation of theta in the positive direction. And the reason it's positive is because this is noted parenthetically. So anything inside parentheses is opposite day to that variable. So my theta is now going to increase by 5 pi over 6, which means I'm going to take this circle, my polar graph circle, and I'm going to rotate it counterclockwise 5 pi over 6. That is, I'm going to move in the positive 5 pi over 6 direction. So if I think about me just rotating this picture here, what's going to happen is this line right here, or actually this single dot, is going to rotate 5 pi over 6. It's going to rotate this direction. It's going to continue to rotate, just turning it just like a wheel until I get to 5 pi over 6. All right, then, likewise, the red line now is perpendicular, I should say, was perpendicular to this spoke right here. It's now going to be perpendicular to this spoke right here. Right, so as I turn the wheel, the red line will now then appear right like that. That's supposed to be perpendicular, pretty close. Anyway, so this red line, the second red line that I drew, is now my answer. That is the graph of r cosine theta minus 5 pi over 6 is equal to 4. Another way to look at it is that this negative means counterclockwise or anti-clockwise, as Mr. Fulb says. And if it's plus, it's clockwise. I prefer to think of it as just the opposite operation to theta. Okay. All right, let's talk about roses. And they always occur in this form, a cosine n theta, a sine n theta. And let me just tell you a couple of things about this. So a is the petal length. It's the length of each one of the petals of the rose. and n is the number of petals. Now, you got to be careful here. If n is even, there are 2 n petals. And if it's odd, that is actually just the number of petals. So we'll work through a couple of examples here. Now, regardless of the graphs that we do in polar, cosine always implies symmetry to the x-axis. So if there's a cosine in the problem, unless you've rotated it, originally, before you rotate it, this is symmetric to the x-axis. Now, I know we're graphing in polar coordinates, but it's going to be symmetric to that axis right there. Likewise, then, anything with a sine in it will be symmetric to the y-axis, which is going to kind of help you get this drawn in. All right, so let's do a couple of examples for these roses, and then we'll move on to something a bit more complicated. All right, we'll try this. 2 sine 3 theta. All right, so every petal is going to be 2 units long, and then 3 indicates that I'm going to have 3 petals. Now, keep in mind, this is a sine curve, so this is y-axis symmetry. So there are 2 ways to draw a 3-petaled rose symmetric to the y-axis. Sketch them quickly here. I can have it pointing up, something like that, very roughly drawn. That's pointing down, rather. I can also have it pointing up. So the question is, which one of those is it? Now, these shortcuts are designed to allow you to graph these quickly without doing an r theta table. However, there are questions whether it points up or down, so you're going to have to do just one entry in an r theta table, as opposed to many, many entries in an r theta table, and you're going to choose an angle that will indicate whether it's this graph or this graph. So I know that one of my petals has to occur along pi over 2 or 3 pi over 2. You can choose either one that you like, so I'm going to choose pi over 2. Also, because it's symmetric to the y-axis, I'll choose the y-axis. I plug in pi over 2 into this equation right here. That is the sine of 3 pi over 2 times 2. So the sine of 3 pi over 2 is -1 times 2 is -2. Now, you got to be careful here. That means if you are pointing up along the y over 2 axis, this is telling you to back the truck up 2. So I'm pointing up, but I back up 2, which means it has to be this graph right here. All right, now, when you sketch this in, you're just going to sketch it in roughly. This essentially looks something like that. Just make it petally looking. Now, all the petals will be equally spaced around the unit circle, which means each petal will be 2 pi over 3 apart. So I've got 2 pi, which is a single rotation, 3 petals, or 2 pi broken up into 3 equal pieces. That's 2 pi divided by 3 radians apart. Now, if I pull this down just for a second, I'll put it back where it belongs in just a sec. But one of the ways you can do this is if you're looking at the number of spokes around this wheel that divides up 2 pi over 3, you can just start at 0 and just start counting over. So I've got 1, 2, 3, 4, 5, 6, 7, 8 spokes between petals. Again, there are 8 spokes between petals, and I'm just counting from 0 here all the way over to 2 pi over 3. So there's 1, 2, 3, 4, 5, 6, 7, 8 spokes between petals. All right, so I'm going to start at 3 pi over 2. I'm going to count over 8 spokes. I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got another one right here. So I'm just going to go ahead and draw that in. I've got my second petal right there. And I'll count over 8 petals again. 1, 2, 3, 4, 5, 6, 7, 8. I've got my third petal right here. Poorly drawn, but you get the idea. 3-petaled rose, 2 units long. Here's your answer. All right, the last group of shapes are the most difficult or the most involved. It's a limicon, dimpled limicon, and a cardioid. These are 3 horribly drawn graphs, but you get the idea. All of these are symmetric to the y. The ones that I'm going to be giving you will not be, but I just want to point out a couple of things about these shapes that will help you get these graphed. First of all, the point of the shape. This is what I regard as the point of each one of these shapes. So I call that the point. It's not really pointed if you were to actually graph it. It's more rounded. It actually is rounded. But I think of a cardioid being like heart-shaped, then certainly this would be the heart-shaped point if you were to draw it typically like a Valentine heart. Okay, so when I refer to the point, that's what I'm talking about. And then all of these graphs will be in one of these forms. A plus or minus b sine theta, a plus or b cosine of theta. Now, as I said on the previous page, if it's got a sign in it, it's symmetric to the y-axis. If it's got an x in it, it's symmetric to the x-axis. That's still going to hold true for each of these. The other part is these signs in between here, and those signs indicate the direction that the shape points. So let me give you an example. If I had a graph that looked like this, or not a graph, but rather an equation, r is equal to 2 plus 3 cosine theta. First of all, I know it's going to be symmetric to the x-axis because of the cosine here. And then I look at this point right here. It's positive, which means this shape is going to point in the positive x direction. It's going to point to the right. So again, it's the sign in between and this trig function right there, which indicates the direction of point. Now let's take a look at 2 minus 3 sine theta. Again, it is symmetric to the y-axis, and this is negative, which means this shape is going to point downward because it's negative along the y-axis. Doesn't matter what the sign of the first number here is. It could be plus, it could be minus. It's still all about the sign in between the two constants and the trig identity. Not the trig identity, the trig function. Okay. Okay. Here's a table I made up. It looks pretty complex, but I promise you, once you get the hang of this, it will come very, very easily to you. So let me just read through this and kind of explain what I have written here. So first of all, they are all in these two forms. We've already talked about that. To identify whether it's a limicon, dimpled limicon, or a cardioid, it's all about the relative magnitude of A and B. So if A is less than B, it's a limicon. A is greater than B, it's a dimpled limicon, and A equals B, it's a cardioid. Okay. And then the point of the shape, we talked about that in the previous page, is indicated by taking A and B and just adding them together. And we also know where they point. The dimple or the loop, which is important for a limicon and a dimpled limicon, can be found by just subtracting A and B. The conjugate axis, and now the conjugate axis is this distance is right here. It's like the perpendicular axis. So if I have the axis of symmetry, let's say on this dimpled limicon right here, the conjugate axis, this right here, will be in green. This will be the conjugate axis. So I guess I should have drawn it with green pointing right there. That's the conjugate axis. It is the axis that is perpendicular to the axis of symmetry. That is A units each way from the pole. And then I've got, of course, got some examples here. So the first one, excuse me, 1 plus 2 cosine of theta. 1 plus 2 cosine of theta, first of all, it points to the right, rather, because it is a positive cosine function. So it points to the right, and it points out to the right. How many units? It is 3 units, because I take 1 plus 2. That gives me 1, 2, 3 units. That is horribly drawn. All right. Then the dimple or the loop will be A minus B. So I take 1 minus 2, that is negative 1. Again, we're just talking about distance. I know it's a limicon because B is greater than A, so it is 1 unit toward the point of the shape, which is where that is right there. And then I've got the conjugate axis, rather. That is 1 unit up and 1 unit down because it's perpendicular to the axis of symmetry. That's where these two come from. And then I also know that limicons and cardioids touch the pole, and then I just kind of sketch it out. All right, let's get rid of all this, and we'll do a couple of these. I'll keep this table on the screen here. And then we'll work through these as well. Okay, so let's do the second one there. I've got r is equal to 2 minus 1 sine theta. Okay, a couple of things about this. I know it's symmetric to the y. I also know I have a negative sign in between, so it's going to point downward. How many units will it point downward? Let's just go through here one at a time. It is a plus b, so it's 2 plus 1. It is 3 units downward. Now, the nice thing about cardioids, limicons, and dimpled limicons is that you can graph it on rectangular paper or polar paper. It makes no difference. I'm going to go down 3 units. That's the point of the shape. It points downward. I also know it's a dimpled limicon. The dimple will be found by taking 2 minus 1. That is 1 unit. So dimpled limicons are like inflated hearts. So it's on the opposite side of the pole. I'm going to have another point up here, 1 unit up. And then lastly, the conjugate axis. I take 2 minus 1, that is 1 unit to the left and to the right, so it's going to hit here, and it's going to hit here. Now, when you draw this in, you just have to make it seem as dimpled limicon-y as you can. So it's going to come up here, try to give it a little something like that, and make sure you hit all the points. And that is going to be your graph. See, I told you it's pretty easy. All right, let's do the last one there, 2 plus 2 sine theta. You can already see from the drawing there what it's going to look like, but that's all right. We'll go through it out together. Y-axis symmetry in the positive direction, so it's going to point upward. How many is going to point upward? Well, it's going to be 2 and 2. That's 4 units up. So I've got 1, 2, 3, 4. I know the point of the shape is right there. All right, let's talk about the dimple of the loop. You take a minus b, that's 2 minus 2, that is 0 units. That's right, cardioids don't have an inner loop, which means it's going to be right here at the pole. Conjugate axis. I take a units each way, so it's 2 units to the left and 2 units to the right. So it's 1, 2, 1, 2. It's going to hit here and here. And then I just connect up all of those dots and make it look as cardioidy as I can. I don't really get caught up into how it actually looks. I just want you to make sure that you hit it. That's supposed to be symmetric to the y. Let's use our imagination and think that it is. Excellent. All right, let's just do one more to make sure we're good here. 2 minus 3 cosine theta. So I've got a cosine, that is x-axis symmetry, and I've got a negative. That means it's going to point to the left. How many units? It's going to be 3 plus 2. It's 5 units, so it's 1, 2, 3, 4, 5. I know it's going to hit right here. By the way, this is a limicon because A is less than B. Okay, then the dimple or the loop. So this is a limicon. Dimple or the loop is going to be in blue. That is 2 minus 3. That's 1 unit. I know it's a limicon, so the loop is on the same side as the point. I've got that right there. All right, I also know that it goes through the origin, because that's what limicons look like. And then the conjugate axis. I take the conjugate axis, I do a minus b, that is a units up and down, so it's 2 up and 2 down. So 1, 2, and 1, 2. Got a dot here and a dot here. And then what I want to do is just connect up all 5 of those dots and make it look as limicon-y as I can. And it comes up here, around through the pole, creates an inner loop, comes up to there. Try to make it look as symmetric as you possibly can. And that's it. Limicon pointing to the left. All right, I got one more thing to show you. Stay tuned. All right, so the last thing I want to go over is finding slope, rectangular slope, of a polar graph. A heading so long it won't fit on one line. All right, so let's start off with this equation, which, by the way, since we're talking about it, looks like a cardioid, because 2 is equal to 2. It's going to point in the left. It's going to point to the left because it is a negative cosine, 4 units. It's going to hit here, 2 up, 2 down, and it's a cardioid. It's going to hit the origin, so it looks something like that. All right, and I'm looking for the slope machine of that graph, and the slope machine in rectangular form. Remember that slope is dy over dx, but in parametric, it was dy over dt over dx over dt. It's going to be a similar process here, except my dy now will be dy over d theta, and my dx will be dx over d theta. And if I copy dot flop, I do get dy over dx. So those two are algebraically equivalent. Now, before you get to determining what this expression is, I need to back up here just a little bit and make some room. And also remind you that x is equal to r cosine theta and y is equal to r sine theta. Because look, I have to have the change in y with respect to theta and the change in x with respect to theta, which means I need x's and y's all in terms of theta only. I don't have that here. I've got these bothersome r's in both of these cases. How do I get rid of the r's? Hey, right here. I can take those r's and plug them into both, which is going to give me then x is equal to 2 minus 2 cosine theta times the cosine of theta, and y is equal to 2 minus 2 cosine theta times the sine of theta. I'm going to use that instead. So these are gone. I'm going to use those two. All right, now, I don't think it saves you any time to distribute that out. You're still going to be stuck with the product rule at some point. So let's just continue the way it is. dy d theta is the derivative of this line right there with respect to theta. So it's product rule, right? So I've got the first as is, which is 2 minus 2 cosine theta times the derivative of the sine of theta, which is cosine of theta, plus then the derivative of the first, that's going to be 2 sine theta times the sine of theta over dx d theta. So now I'm going to derive this line right there with respect to theta. And that's going to give me the product rule again, right? So it's going to be the first. That's 2 minus 2 cosine theta times the derivative of the cosine of theta, which is the negative sine of theta. I'm going to add that then. 2, that's going to be 2 sine of theta times the cosine of theta. Excuse me. So if I wanted to see what the rectangular slope was at, say, theta is equal to pi over 2, I don't even need to simplify this. And by the way, I can't cancel top and bottom because I've got a sum in the top and a sum in the bottom. But if I'm looking for the slope rather, at theta is equal to pi over 2, my dy over dx, again, what I'm doing is I'm taking pi over 2 and I'm plugging in wherever I see a theta and evaluating them. And it looks like I got 0. It looks like I have 2 on the top. And it looks like I have negative 2 on the bottom. It gives me a slope of negative 1. Now, if I go over here to my picture, it looks like, and I draw that in, oh my goodness, it's a slope of negative 1. It's a little bit, it has to do with the way I drew it. I really should have drawn it maybe like this. It's a little more swollen, a little less pointy. So it stands to reason, had I drawn it to scale, that the slope should be negative, and negative 1 does seem reasonable. All right. Now, one last thing. Let's say I'm looking for points of vertical tangency on my graph. So vertical tangency. Well, vertical tangency implies that it has undefined slope, which means the denominator is equal to 0. I have undefined slope. So what I'm going to do is I'm going to take this denominator and I'm going to simplify it. This gives me negative 2 sine of theta plus 2 sine theta cosine theta. This is going to be plus 2 sine theta cosine theta is equal to 0. So I'm going to set the bottom equal to 0 and solve it. This looks like negative 2 sine of theta plus 4 sine theta cosine theta is equal to 0. I think I'm going to take out a 2 sine of theta. That'll give me negative 1 plus 2 cosine theta is equal to 0. And I'm going to t it. So it looks like theta here, when I divide by 2, that gives me 0 and pi. And then when I set the second one equal to 0, that gives me the cosine of theta is equal to positive 1/2, which looks like it's going to be in Q1 and Q4. So my theta looks like it's going to be, what is that, pi over 3 and 5 pi over 3. So now I'm looking for vertical tangency. If I do this in green, pi over 3, 5 pi over 3, it looks like it gives me 2 points on that curve where I've got a vertical tangent line. And then I've got 0 and pi. Looks like pi is totally good, but at 0, the problem is with this problem right here is I have a cardioid, and this actually is a sharp point right at 0, so I need to take that off. So I think it's helpful to sketch the graphs. You will have sharp points for cardioids. So any sharp point will have no slope there, so you need to take those out. It's an extraneous solution. I've got then vertical tangent lines at theta equals pi, pi over 3, 5 pi over 3. Guys, I hope that gets you through tonight. Sorry this took so long. Thank you so much for hanging in there. Hope to see you soon.